Our first talk is Sandy Clark doing Familiarity Breeds Contempt, and she is joined by Matt Blaze.
Thanks, Crimson. So we're going to be talking, can you go to the next slide? Yeah, we're going to be talking about probably the most ignored area of computing security research, and that's metrics. One of the things that we are terrible at doing, in addition to securing computers, is we're also terrible at figuring out how badly we know how to secure computers. And there's a fundamental question that we have largely ignored through the history of computer security as a research field, which is a very basic metric of how can I predict how long it's going to be before I get attacked next? That is, how long is it going to be before somebody finds the next zero-day attack in my software? And we know there is going to be a next zero-day attack. We've figured out there is one metric, a security metric for software systems. None of them are secure. But we don't really know how to compare them, and we don't really know where in the life cycle we are in a piece of software. And does anybody, can you go back to that slide before? Does anybody recognize this graph? What's that graph? From the Mythical Man Month. This is as close to biblically given truth that computer science and software engineering has about the software life cycle, which is at the beginning of the life cycle, right after you release your software, it has lots of bugs in it, the easy ones, and you find them quickly. And as time goes on, that rate of discovery of bugs goes down. And then after a while, it starts going up again. A long time later, when some of the more esoteric bugs start to be discovered and when environments change and the software gets stressed in surprising ways way in the late. But essentially, the important part of this curve is, for most of the life cycle, your bug discovery rate should be going down. And it turns out this graph from back in the ancient history, like the 1970s, before our great-grandparents were programming, has been remarkably stable over time. People have tried to measure it and discovered exactly the same thing. You get this decreasing rate of bug discovery. And one of the kind of fundamental basic questions is, does this tell anything to this computer security community? Do we observe the same thing about the vulnerability discovery rate? That is, we have this sort of basic assumption that vulnerabilities are a form of bug, and that if the Brooks curve applies to bugs in general, well, vulnerabilities should just be kind of randomly distributed in there, and should have the same behavior. And that leads to a number of really basic assumptions. The most important one is whatever you're doing to reduce the number of general bugs that you've got will help you make your software more secure in practice and reduce the chance or increase the amount of time before that next 0 day in your software is discovered. That is, better software is better. Better software is more secure. That seems sort of obvious, and it seems like it should follow directly from the basic precepts of software engineering that Brooks told us. So we set out to answer this question. Are vulnerabilities just another form of bug? And the short answer is no. And thank you very much.
Okay, so thanks, Matt. So what we did is that we just collected a whole bunch of vulnerabilities and then we counted stuff. And what we found is that there's sort of a honeymoon that goes on when software is new, that is very different from the behavior of software when it's older. And this is going to have some important implications. Instead of the Brooks curve, which is the graph you see on the left, what our data shows is that when you're looking specifically at vulnerabilities instead of at defects, that you have this long relative period before an attack, and then the rate of attack goes up. And to give you an idea of our data set, we collected 30,000 vulnerabilities, and then for all of those we looked at, we compiled a list of the most popular OSs and software apps and server stuff and user stuff, anything we could think of, and we ended up with 700 different releases. And we looked at the date of actual release to the very first vulnerability to the second vulnerability, the second to the third, and the third to the fourth. So we didn't do any fancy statistical analysis, we just measured days. And what we found is that contrary to the software reliability models like the Brooks curve, at the earliest part of their life cycle, there's this honeymoon. So what do we mean by a honeymoon period? It's this time, the time from release to the time from the discovery of that very first 0 day. And here, because there was such a high variance, every different product has a different release cycle, we normalized the data by using the ratio. We took the number of days from release to the first vulnerability, and we divided it by the number of days from the first vulnerability to the second vulnerability. And we called that a positive honeymoon if the ratio to the first vulnerability was longer than the ratio to the second, and a negative honeymoon if it was the other way around. And here's some of what we found. 62% of the releases we looked at had a positive honeymoon. That means the time to the first vulnerability was longer than the time to the second honeymoon, or the second vulnerability. And even more important, the length of that time was rather long. The median number of days before the first vulnerability was discovered was 110. So they take a while to find. And even more, at the beginning. This is, we didn't look at all later on in the life cycle. This is just very early. And even more importantly, they take a lot longer to find than it takes to find the second vulnerability. The median overall honeymoon ratio was 1.5 times longer to find the first one than it was to find the second. And this is exactly opposite what the software reliability models would lead us to believe. So there's this honeymoon effect, and now we had to figure out why. At first we thought, well, you know what? Software has gotten better. Since the 1990s, there have been a lot of changes in the way that people develop software. We now use type-safe programming languages. Things like Microsoft's Software Secure Development Initiative, and we do our own fuzz testing. So we broke it down by year, and it didn't make any difference. Now, our software reliability models tell us that we should find that there are very few positive honeymoons. Not that there is a minimum of 50% or greater. And it doesn't matter what year we look at. 2007 had 71% of the honeymoons were positive. And not just breaking it down by year, it didn't matter how we broke it down. If we looked at just open source versus closed source, if we looked at server apps or operating systems, if we looked at major releases versus minor releases, consistently positive honeymoons. The first vulnerability takes longer. So we need to pause for just a second, if I have time, and consider the implications of this. The fact is that software is likely to enjoy this honeymoon from attack, even though none of its bugs have been fixed yet. Every single bug it's got in it, it still has. No one's found any. Even the easy to find ones, even that low-hanging fruit, are still there. This is exactly opposite, because by definition, when the software is new, it's at its weakest. But it's precisely at this time, when it is at its weakest, that it's least likely to have one of its vulnerabilities discovered. And that means that we're looking at this wrong. Something different than just fixing bugs is going on here. And what we figured out is that it's a difference between extrinsic and intrinsic properties. Intrinsic properties are those things that the developers and the programmers can control. What programming language they use, their initial design of the software. But because of the way that we analyze the data, we were looking at vulnerabilities only within a single release, and each release independent from another. If there are going to be improvements in software quality, they happen between releases, not in the middle of it. So this has to be something that's extrinsic. Now, there are a lot of extrinsic properties that affect software. They can be anything from the operating system and the architecture it runs on, to its network interfaces, to the other applications that are running on the system, to the black market in how much the particular vulnerabilities for this particular application sell for. We have no idea what all the extrinsic properties are yet. They're not well defined, they're not well understood. But it occurred to us that the majority of these extrinsic properties cannot be responsible for this, because according to all of the data about exploits, about vulnerabilities, things are getting worse. The attacker side is winning this arms race. So if the majority of these extrinsic properties were responsible for the honeymoon, we should see positive honeymoons drop to 0. We should see it getting shorter and shorter and shorter. So we started looking for clues. There had to be something, but we didn't know what. The first difference that we found at all was when we compared major releases to minor releases. The difference between a major release is that a major release is intended to sell a new product. It has new features, it has lots of changes, and it has the majority of the new code. Minor releases are almost always bug fixes. When we examined the difference of the data, the positive honeymoons in major releases rose from 62 to 72%. The median length of the honeymoon rose by 9%, and the honeymoon ratio rose from 1.54 to 1.8. In other words, major releases have more positive honeymoons, and they have a longer honeymoon period. So where there's more new code, you get a longer honeymoon. The second indication came when we compared open source code to closed source code. If I will quote from an Android designer, Android people, they say, have the freedom to have no legacy. What's interesting about the open source to closed source is that it has a longer honeymoon period but a shorter honeymoon ratio. Well, open source releases versions far more frequently than closed source does, and they change their code a lot more. So that means that not only is it taking attackers longer to climb the learning curve, but they're not doing it with frequency in the next vulnerability as well. So here's our hypothesis. That honeymoon period we're talking about, that's the attacker's learning curve. That's the familiarity they have with the code they're trying to attack. And what we think is happening here is that knowledge gained from finding that first vulnerability is used to help find the second vulnerability. Tools that are developed can be reused. And we also think there may be a blood in the water effect going on here. Somebody found a vulnerability in X, so everybody starts focusing their attention on X, thinking that they can find one too. And it turns out that there are also two kinds of that very first 0 day. There's a vulnerability that you expect. New code is buggy. None of us write good code, well, I don't write good code. And I expect that I'm going to be introducing new bugs. So this, what we call a progressive vulnerability, is one that occurs as a result of putting in new code. But we found that there were a lot of what we're calling regressive vulnerabilities. These are vulnerabilities that we found in version X, but they affected X minus 1 and X minus 2 and X minus 3, which means they had to be introduced in X minus 3, especially if they didn't affect X minus 4. These regressive vulnerabilities lay dormant for quite a while until they were found. And one would expect that there wouldn't be very many of them, but there are. Most of the first vulnerabilities that are discovered in a piece of software, in a newly released version of a piece of software that's been out for a while, affect the earlier versions as well. So most of these are regressive. This is code that attackers have had time to look at. This is code that they've been familiar with. And the most interesting thing about this to us is that even though this code's been out there a while, even though they were able to attack it faster than maybe they were able to attack the new code, there's still a positive honeymoon. It still took them longer to find this regressive one than it takes them to find the next vulnerability. It appears that even when you reuse a lot of code, there are enough changes that you increase the attacker's learning curve. And other data is that progressive honeymoons even last longer, almost over twice as long. So if you introduce a lot of new code, you can double the time it would take for an attacker to be able to successfully exploit a vulnerability they found in your code.
Right. So just to put a double underline on that, the single important message of this talk is new crappy code is more secure than old good code.
Even if it introduces new vulnerabilities. Right. So the thing that we think is happening is that new code acts as a driver, and this driver extends your honeymoon. It forces your attackers to take time, it forces them to expend resources, it forces them to rewrite tools, it forces them to relearn how to attack your code. No, 5 minutes? Okay, we're almost done. Anyway, so what does this teach us? Vulnerabilities are not the same as bugs. And the reason they're not the same, hold on just a second. The reason they're not the same is because their extrinsic properties are different. When we think about the extrinsic properties of a software defect, you buy a piece of software, your extrinsic properties are written on the box. It needs this operating system. It needs this kind of architecture and so much RAM. They're static, they're well understood, and they never change through the life of that software product. But the extrinsic properties that affect whether or not it's going to get attacked, we can't even list them all. We don't know them. They're not well defined. They're not even well understood yet. That trying to figure out the characteristics of and to delineate those extrinsic properties is part of the work I'm trying to do right now. They can be anything from attacker interest in incentives. They can be network presence. They can be how the inputs are processed. We don't know. So why is this important? Well, realizing that familiarity, this extrinsic property, this learning curve, causes the honeymoon effect, means that we have the first tool that we can use to actually measure how secure, our relative security, there is no such thing as security, but possibly how long it's going to be until we can get attacked. When I buy a safe, for example, I buy a safe according to a particular rating. A safe with a 30-minute rating is good against all known extrinsic properties, that is any possible known attacker tool, for 30 minutes. So when I develop my security strategy, I do a defense in depth and I have my security guard walk around every 29 minutes. We need the same thing for software, and that's what we don't have yet. And that's what we think that the honeymoon effect is an important part of developing. The other thing that we want to be able to do is knowing that's a honeymoon effect, software developers need to figure out how to prolong it. What about dynamic execution? What about obfuscated binaries? Anything that extends the attacker learning curve. And lastly, we can't just throw out all our code and rewrite it from scratch, but maybe that would be what, the best way to do this. Every 3 months, throw out your code and just rewrite a crappy version. So what we have to do is we have to decrease the value of familiarity to the attacker. The old code never goes away. It's much too expensive not to reuse, but it really matters to the honeymoon period. Windows 7, for example, didn't have a honeymoon. On the day it was officially released, don't remember what labs, Sophos Labs, I think it was, grabbed the first 8 or 10 vulnerabilities they had in their honeypot, and they were for Windows Vista, and tried them out on Windows 7, and they all worked, and it was all because of code reuse. So the best thing that we can do to hope for existing systems is to make enough changes that we keep the attacker in a perpetual learning curve, make their tools unusable, and this would give all of our code a second honeymoon. Thank you. And we have a question in the back here.
Yeah, quick question. Have you done any research into this honeymoon period in comparison with the adoption rate of the software?
We're actually looking into that now, and I have a position paper coming out on that very soon, like within a week.
But it's more than that. We didn't compare all the honeymoon stuff we did is comparing software with bugs found in the same software
Right.
later. So it's normalized for each particular piece of software within itself, which is why we're using the ratio rather than the absolute number of days. Right.
Well, the thing I'm curious about is you mentioned Windows 7 being exploited right away. Windows 7 also had an adoption rate, which was pretty much instantaneous. It pretty much went to ditch next to this.
Right.
So the profit for attackers for Windows 7
Was high.
Right.
Right.
And
Yes.
when we're talking about, I don't want to be too snarky, but when we're talking about bugs in Windows, I mean, it's unfortunate our data only had a resolution of 1 day. It's possible that you need minutes.
Good. Go ahead.
Consider the element of observation of a 0 day listing. That's how long it took to find the 0 day.
We understand.
For 0 days, I'm not going to use all in 1 day.
We understand that, and that makes the data even more interesting because they could have, however long they've held out until it was found, that honeymoon is still longer. The one thing that we can't measure is what people are finding and holding on to. So this is a best that we can do. But metrics is a hard thing for CS to develop right now. Go ahead.
If you change the definition of your honeymoon period to when the vulnerability is first introduced into the code, does that change your perspective or have to look at that?
Well, one would assume that the vulnerability is introduced when the code is written, correct?
But you were talking about vulnerabilities that exist back in Vista that were actually
Right. So we're looking at the, right, so we're looking at the time before the a vulnerability is discovered and turned into an exploit.
It sounds like in the most
Right.
recent release of software, you're starting to suggest that it's actually
Right.
vulnerable.
Yeah, so are we. In the case of progressive vulnerabilities, definitely.
Right.